Suppose you have a meeting in next 10 minutes, but you are still at the entrance of parking lot, waiting 3 or 4 cars in front of you to get their parking tickets. You may not attend the meeting on time. You must be struggling with long queues while the attendant is busy with calculating fares. Suppose you are very lucky. You find a parking space quickly and run to the meeting. However, I believe you don't have time to remember the parking position in such a rush time. After a long, tired meeting, you come back to the parking lot and find out you can't remember where did you park your car. Well, in our system, people could have a great experience. We set router, conduit at first floor, X-dot ultrasonic on each floor. Uh, as you can see, this is the first floor setting for the parking position detection. And here's the second floor setting for the parking detection. When a car enters the parking building, the web camera takes a picture of the car plate. License could be recognized and stored in the cloud, so you don't need to stop and wait for tickets. Once you drive into this building, your plate license will be uploaded to the cloud automatically. After the car enters the parking building, it's time for X-Dot to work. Ultrasonic and X-Dot on each floor will detect whether the car is going through this floor or not. After aggregate each floor's X-Dot message, cloud will calculate which floor this car is parking on and bond it with the plate number we have saved in the cloud. In the end, we will have a dataset including all the license plates that enter this building and their corresponding floor position. It's easy for looking up position. As you can see this car parked on the second floor. It will show in the result and saved in our cloud dataset.
Let's go back to the start of this experiment. We run a Python script which uses a camera, capture the image while the car is entering the parking lot. And after getting the image, the script will run YOLO V3 system, which gets the plate image part. Then, using convolution neural network to recognize the plate number. After getting the plate number, we upload it to IoT dashboard. So we can see from the screenshot, the license plate and data has been successfully uploaded to IoT part. So this is a part for plate detection and uploaded to the IoT system. The following video is for the second experiment, which is exactly the same as the one before. There are overall 4 steps for the entire plate detection procedure. First, the YOLO v3 license detection. YOLO v3 stands for You Only Look Once. It's a general real-time object detection algorithm. This avoids spending too much time on generating region proposals. It's a convolution neural network. The second one is word segmentation. We will segment the plate number or words into pieces. Next step is word recognition. To recognize each piece of word, the last step is output our plate number and upload this information with timestamp to S3 bucket. So the mechanism of YOLO algorithm is transferring object detection to a regression program, which contains bounding boxing program and associate class probability program, which means each detected object is bounded by a box with a probability. Bounding box and class probability are predicted from full image by convolution neural network and a no maxing suppression. So the output of YOLO system is our license plate image. So after locating the license plate and get the license plate image, The segmentation is adopted to extract characters in the license plate. First, change the license plate image from RGB to grayscale. The next step is to binarize and blur the image. The last step is use find contour method to extract each character in this license plate. The last step of the ALPR is character recognition. Each character in the license plate is recognized by convolution neural network. So here is the convolution neural network frameworks. The CNN applies convolution process to extract important information from image. Each convolution process can be considered as a filter. After convolution, the fully connected neural network with ReLU activation is used to classify the character in the license plate. So the first layer is convolution layer, which implements valid padding. Valid padding is to reduce the dimensionality as compared to the input. The next layer is max pooling layer with a max pooling operation. This is to decrease the computational power required to process the data through dimensionality reduction. Return the maximized value from the portion of the input data. Then followed by one convolution layer and one pooling layer. Then come to the classification part, fully connected layer. So right now, we have convert our image to a suitable form for the neural network. We will flatten the image into a column vector. Then flattened output is fed to a neural network and trained. The way this fully connected layer works is that it works at the output of the previous layer and determines which features most correlate to a particular class. This class is single character of words and numbers. So after get the plate number, we will upload this plate number to the S3 bucket.
Let's go back to the beginning of the experiments.
We place ultrasonic sensors with X dots on 2 floors. Each floor has one sensor with one X dot. When the car passes the ultrasonic sensor, the sensor will detect the change of distance and change the signal value. Then, the sensor will send the signal value to the X dot. After getting data from the ultrasonic sensor, the X dot with specific identification number sends a message which contains its ID and whether the car is passing this sensor to the conduit. The X dot cannot communicate with AWS IoT core directly, so we have to first send the message to the conduit. The conduit is used as a gateway to connect X dots with AWS IoT. It communicates with X dots by the LoRaWAN, which stands for low power. In Node-RED interface of the conduit, we can see the message sent from the X dots in the debug window. After the conduit receives this message from LoRaWAN channels and adds current time information, the conduit sends the message to AWS IoT by MQTT channel. When the AWS core receives data from the conduit, it will display it on IoT core.
In here, I will quickly go through the detailed implementation of car trace detection. The architecture we used is the X-dot sends the ultrasonic sensors information to the conduit, and the conduit works as a gateway and send the message to the IoT. To communicate between the X-dot and the conduit, we will use the LoRa. The LoRa library is provided by the embed. So here it is the LoRa library. We will import this library in the compiler and set it as the following. In here, this is the property of the LoRa connection. We want to set those property be the same as we set in the conduit part. So the next step is to receive the ultrasonic sensor data. Receive data from the ultrasonic sensor. So we'll have the class called HCSR04. This class just initializes the ultrasonic sensor and send the wave to the object and get the bouncing wave from the object, and use those wave and the speed of the voice to calculate the distance between the ultrasonic sensor and the object. In here, we will power up our sensors by setting the trigger point as GPIO 0 and the echo point as GPIO 2. And we will give each X dot a specific ID and format our message like ID, comma, whether the car is going through. So if there is a car going through, we want to have the threshold less than 150 centimeters. If if the distance calculated by the ultrasonic sensor is more than threshold, there's no car coming through. And the next one we want to illustrate how the message sent from the conduit to the IoT. So in the conduit, we use node-RED. This is the flowchart of node-RED. The conduit receives the signal from the lower channel, and we pass through a format function, which will add the timestamp to the message we will send to the IoT. And we use the MQTT connection to send the message to the IoT, AWS IoT. And in here, it shows our message looks like. We have the ID, location, and date time. In here, we want to illustrate the IoT, AWS IoT receive the signal. So here is a very dummy testing. It's called things x.01, which is same to we set in here topic things x.01. As you can see here, it is our flowchart of cloud parking localization in the cloud. After webcam pushing license plate data and conduit pushing car trace data into AWS IoT core, we apply AWS rules to select those newly updated data, and forward them into AWS S3 bucket. AWS IoT core is similar to the database, so we use simple SQL language to select those data. Then the Lambda function, we need to separate license plate data and cartridge data into their own bucket in the S3. After all the bucket get data, we apply another Lambda function to finally decide the car parking position.
Next part, we will show how it works in our project.
In here, we will show our implementation in the AWS and how we compute the car parking location finally. So in the AWS IoT core, we will create two things. The first one is called camera, which is used to store the license plate data. The second one is x.01, which is used to store the car trace data. So we want to use this data in the Lambda function. So we certainly want a trigger to push those things into the Lambda function. So the trigger is the AWS rules. We have two rules here. The first one is called parking, which selects the license plate data. As you can see here, it's a simple SQL to select the data from the same camera. Another one is called location. It's also same to the license plate data. It's used SQL to select the data from the things x.01. So we will go to the Lambda function. The first Lambda function we will use is called parking, which push the data into S3 bucket. As you can see in the designer here, we have the IoT rules, which is trigger, and which is the trigger of the parking function over here. So this is our code. In the code, we can say we have the events. In the events is just data from the IoT. If the license plate in the event, we want to push this license plate data into the license.json in the S3 bucket. if the ID in the event, we want to push those ID number into S3 bucket, but we have different X dot, and each X dot have its own ID number. So if 0 is the ID number, we will push it to the X dot 1. If 1 in the X dot is 1 is the X dot ID, we will push it to the X dot 2, similar to the number 2. So the last part the last part is to classify or specify the car parking position. This is our another parking position lambda function. In here, we will take all the data from the S3 bucket into our function. So the first one in here, we will get the license plate data. Then we will read the x.1 data and x.2 data. And then we will end with some binary representation, for example, 00, 10, 01, 11, to classify or specify our car final location. If the input is 00, we will have our car parked at floor 1, similar to the 10 and 01.
The total equipment cost is around $900. Coming to the cost analysis, the cost for the traditional system per month is 3,000. The cost for human resources is 3,000, and we are assuming that the traditional system does not have any databases and in the web, so we are assuming its cost to be zero, and the total cost for our new system is $1,100, because in human resources we don't need human resources because that's the key, and web infrastructure we need to have one cloud database and one server to manage the system, and the cost for new equipment will be $900. So per month, after installation, it will lower to only $200 per month, which is a lot of which is a very good improvement than $3,000. So coming to the ease of implementation, it has very less equipment, low power, less maintenance, and very fast. And we have all the records recorded in our database, so we can do predictive analysis, we can track those things, and it is also easy for the future upgradation. Coming to the USC's thing, USC is the potential customer. So we had a chance to talk to the senior associate director of USC, where they said that they have a problem for recording the car numbers, number plates of every car which is entered to their parking lot. They said that they have problem doing this because it's human-prone error, and they were saying that they need a system where they can scan the cars when they are entering the parking lot, and they can able to segregate all those things as reserved and non-reserved parking, and the paid and non-paid ones, and they also wanted to remove the human prone errors, and our solution is a best suitable solution for us. Our system is the best solution for the problem, where we have a scanner. When the car enters, it scans on its own, and all the car number plates will be stored in the database, where they can have it as a record in the future.
How our system is implemented, now we can show how it can be extended. So one of the extensions we have is collecting data about the exact parking spot and showing that. So the system for now can only show in which floor the car has parked, and to support showing the exact parking spot, we need to only add X dot to each parking spot. This solution is scalable and can support up to 5,600 spots for each getaway, given that we're using 8 channels and under perfect conditions. Also, publishing that data, I mean the parking spots to users, is easily done. Since the data is already available, we can publish this data to user either in the parking lot itself, as shown in the picture here, or by making them available online. And to implement that, we need to only add displays in the parking lot and work on user interface integrated with the cloud storage. Another extension is implementing blacklists. So preventing cars from entering the parking lot is one of the extensions our system can support. By integrating the plate recognition node with the drop arm at the lot entrance and also exit, This feature can also be extended to give access to car information to local police department, which can help them in locating stolen cars or even wanted ones. The drop arm at the exit can keep flagged cars inside the lot and then automatically notifying the local police department about those cars. The last extension is doing parking data analysis. Parking data can also be stored for future use. One of the uses is analyzing the data to infer when the parking gets full or how many permits we can issue over capacity. Also, peak hours can be inferred, which can be used to increase the hourly rate or help users in avoiding peak hours. That's it for the parking extensions. So let's go to the next part.
Here are the references we use in this project. And thank you for watching. This is our smart parking system, which will give you perfect parking experience.